And this is the hard one. Okay, so pay attention. So remember that we started with the idea that we are teaching to think in a way to solve problems in an approach that is called computational thinking. And computational thinking basically has this 4 part. We decompose computational thinking in 4 parts. The first part is the composition, that you have a big problem and you separate it in small part. And then second, you try to see how much these small parts are similar together. By the way, this is what we do in the homework that I am giving you of finding the min and max. Patterns, according to the dictionary, are things that repeat, repeated design, or things that are comparable objects, like houses are following. So my point is the patterns are something that for humans is super important. Humans are very good at finding patterns, and maybe too much. Our goal in science is to, well, our goal is to understand nature, but we do that finding patterns in it, things that happen always, like, I don't know, if I eat sugar, I get fat, let's say. If I smoke, I get cancer. There's a pattern there. Not always, but there is a pattern. They are not identical, but they are. So, for example, people found that there is day and night. And a lot of the first knowledge that people have is that after the night, there will be a day. And after the day, there will be a night, and there will be winter, and there will be summer. People notice this pattern for thousands of years. No? And when you understand that there is a time that you have to put the seeds, and there is a time that you have to harvest the fruits, that people who learn to do that, or people who learn to follow the animals to hunt them, or to fish, whatever, people understand. You know that 99% of mushrooms are poisonous, except the one, the mantar that you buy in the corner, that is good one. But the others kill you quickly. So people had to learn that. Which kind of mushroom you can eat, which kind of mushroom will kill you forever. That is a pattern recognition that people develop. And that is what we do. We are a pattern recognition machine, and patterns are important to us. So you find pattern, for example, in the thing that we build. Obviously follow a pattern, no? Houses are following a pattern, or patterns, okay? But we also have patterns in nature, and we want to describe them. For example, here you have different trees. They are not identical, but they follow the same pattern, no? Like here, they have kind of a vertical lines, not identical, but following the same pattern. And we would like to understand them and describe them. I have this pattern. We have a different kind of pattern that go more and more complex, but they follow. We have patterns in art and decoration. You find them. Maybe here you will not hear this thing. Play this one. Okay, I guess that you follow me, no? And we have basic patterns, so loops, if you like, no? This is clearly a repetition. This is not working forever, it's making one work and repeating. It's also a pattern. So patterns, and we see the patterns also in our program. We have patterns like loops that we do the same thing again and again with some small modification, like the index is updating every time. When you draw a star, for example, drawing a star, every corner of the star is essentially the same, just a little different angle. when we write functions, if you want to draw different stars, let's say you're drawing a landscape, you have to draw many stars. So drawing a star is a loop, and draw many stars is another kind of function that you say the same drawing. That is the pattern that we have seen so far, okay? That allow us, for example, you can make a program to draw a house, and you will have to essentially draw the same windows with a loop. If you make a building, let's say, you have to draw all the apartments with a for loop. But there is another kind of pattern that happens in nature and in particular in biology. The pattern that we see here. Can you see the pattern? A pattern that you see in trees, a pattern that you see in rivers, and the pattern that you see in the blood vessels, in the blood system. What is the pattern? Can you tell me what is the pattern?
A model.
What is that? Any guess what is the pattern here?
They all kind of branch out. Branch out.
Some people learn the keyword, they will say, this is a fractal. Some people saw in the high school fractals. But the word that we are going to say here is a pattern that is part of itself. Like the pattern I will say, if you can see me, that a river is made of many small rivers, and the small river has many small rivers. So you start the Amazon, for example, river has two main rivers, and even if each one of them is separated in smaller rivers until you get to the garden, when you put a drop of water, and that drop of water is going down until the Amazon river. And same the blood vessels, they split, they branch in smaller, but the branches are essentially like a small version of the main system. Okay? So a tree has trunk and branches, and each branch is a trunk with branches. So every branch is a little tree. And the same with rivers and so. So the easiest way to define a pattern is to use the same pattern. So this is the trick, like you are talking about something about something. You are using the object to define itself. I am what I am, or something like that. Some people think about the Russian dolls, like the Russian doll is made of a Russian doll that is made of a Russian doll. In computer code, it will be like this. It's a function that here I call example, and you can have some code, but somewhere in the code, it is also using example. The function is used inside the function. That is tricky, but allows you to describe this kind of problem. And this is kind of the super powerful thing, that when you decompose something, when you decompose a big problem, you can realize that the parts are essentially something like the big one. Not exactly the same, but the same pattern. Okay? So you want to draw a tree, you have to draw trunk and branches. And for drawing branches, you need to draw trunk and branches. And for drawing those branches, if you want to describe a blood vessel, if you want to essentially problem that have this pattern, and that's a pattern that happens a lot in biology. Biological networks tend to have this shape. The key word here is recursive function. Function defined in terms of themselves. For example, there is a classical example, not necessarily the correct way to do it, but this is the typical example that you will find everywhere that someone tried to teach this. We can talk later if there are more smart way to do it, but this is for teaching, okay? Very simple. The factorial. Some of you may know this exclamation mark. It's a mathematical formula that you take a number, like say 5, and it means 5 times 4 times 3 times 4, 5 times 4 times 3 times 2 times 1. Okay? And you have like 20 factorial divided by 3 factorial. So people use when they count things in the binomial theorem and so on. When you say, for example, a plus b to the power of n, you will get this n factorial somewhere. Okay? So one way of defining is this n factorial. To calculate the factorial of n, you multiply n, the number that you get, by the factorial of n minus 1. So you define the factorial of a big number in terms of the factorial of a smaller number. So the factorial is the factorial. Kind of, if you do it wrong, it is nonsense, because you are essentially not speaking without telling anything new. But if you do carefully, it can be something. So how we write this in R? A priori, we will do this. We will say factorial is a function that takes a number, and the answer will be n multiplied by factorial of n minus 1. This is essentially this mathematical formula from here written in R language. Okay? Fine?
Where does R know factorials mean?
We're teaching. Good question. How do you know? Because we're defining it here. We are teaching it using it itself.
Okay.
Yeah, good question.
So this is kind of a loop, right?
It's a kind of a loop, but it's a different, because the loop is like, loop is literally, well, okay, this in this case can be equivalent, but in general, the idea is this. Loops are good when you are drawing windows, and all the windows in the building are the same shape and you are doing many times, okay? That is a good loop. This is more like when you are drawing trees, that you have a big one and the small, but you have a change of scale if you want, because you see that this is factorial, but it's not factorial of n. There is a change here. This is n minus 1. Okay?
Okay.
So let me make a visual approximation. We start with factorial of 4. To calculate factorial of 4, we need to multiply 4 by factorial of 3. Okay? And factorial of 3 is factorial of 3 times factorial of 2. Okay, we are delaying the problem. And factorial of 2 is 2 times factorial of 1. And then it essentially can go to factorial of 1, factorial of 0, factorial of minus 1, factorial of minus 2, factorial, and then you get into trouble because essentially you go forever. So the problem that we have here in this very short version is that it will never finish. I will go deep down. Like, you know, there is a old mythology from ancient time that people believe that the earth was a big thing and there were turtles holding the earth. You know that thing? And the question is, the turtles, where are they standing? In other turtles. And the turtles, where are they standing? In other, so they say, turtles all the way below. Turtles over turtles over turtles forever. That was the old theory. The earth is here and there are turtles and turtles and turtles and turtles. Good. Turtles all the way below. So to avoid this infinite turtle problem, we need an exit condition. We need one step that we have to say, if this happens, if this is a simple case, we solve it. So the basic idea is that we decompose the big problem into smaller ones until we get to a condition that is simple, that we can solve easily, like when we have the minimum. So for example, I will give you one example. To find the minimum, not the best solution, but if you want to find the minimum, the smallest of 10 values, you compare the first with the smallest of the first. You can call minimum itself. You take the minimum of the first 9 and you compare it with the last one. And to compare the minimum of the 9, you compare the minimum of the 8 and 7 and 6. You are taking it every time smaller and smaller and smaller. Same logic. but there should be a stop. And the stop, you remember, is when you have only one thing. When you have only one element, that is easy. What is the minimum here? This one, because there is no other alternative. In the case of factorial, the easy solution is the factorial of 1 is 1. Okay? So that will be our exit condition. And also factorial of 0 is also 1. So we can have a generic version. This is a way to do it. So can you see what's happening here? The summary of what I want to teach you today is this. If you want to describe a problem in terms of itself, you can do that, but you have to take care of two things. One, that you have an exit condition. You have one case, at least one, maybe more, but at least one case when the solution is very easy and you know it. You don't have to go one level down. It's like going at different levels. No? So you don't need to go one level up or down. So if n is 0, you get 1. If n is 1, you get 1. If n is bigger, then we go to the second part. And the second part is this. When we take our function and we use it inside, what we do should be simpler. So we start with n. We cannot use n again. We can only use n minus 1.
I have a question. What if n is a number like 5.4?
Well, we will be in trouble. We will be in trouble. But well, eventually, what we have first, we should say, it's not say, you are right, that in the contrary of factorial, factorial works only for integer numbers. That is the way that historically defined. You have a valid question, and in fact, people ask that question, and there is a solution if you want to do. In this particular case, if you take 5.5, let's say, you will get 4.5, 3.5, 2.5, 1.5, and eventually you will get a number that is less than 1, and it will stop. So if you take a negative number, for example, which is also not allowed in factorial, factorial works for natural numbers, okay, for things that you count. Because factorial is something about counting. We can talk longer, but let's go one by one. You are right. This should be used only with integer, but if not using with integers, it will still work. Given an answer that probably is the wrong answer, but it will not go forever. Because precisely for the point that we were saying, the problem, even if you say 5.37, in every step, the problem is simpler in the sense that we are taking n minus 1. And it will be smaller and smaller, and eventually will be less than 1. Okay? And if it's less than 1, we have an exit condition and we stop. Let me tell you the other part. What happened in real life is that if you forget to do this, the computer will get essentially will call a function that call the function that call the function. And since the computer has a limited memory, they have a way to count. They count how many levels you are down. And if you are too deep, they will say, hey, stop it. You cannot go forever. Typically, computers have a limit of how deep you can go. It can be big, but eventually they will say, no, you are doing it too much. You cannot do infinite things here. Okay? So with this condition, now we don't go forever, and we get this version. So factorial of 4, for example, will be 4 times factorial of 3, which will be 3 times factorial of 2, which will be 2 times factorial of 1, will be 1. 1 times 2 equal 2. 2 times 3, 6. This will be 6. 6 times 4, 24. Okay, I'm giving you a hint. This is not valid. I will give you a solution for the homework, but it's not the solution that you can do. This is not the one that I am working for. A way to solve it recursively, the question that we say. Find the minimum, find the smallest value. You enter a vector. This is exactly the question that we asked, but it's not the answer that I'm looking for. So this is not a valid answer for the homework, okay? Okay, there's a question here. Why here we didn't use, why here we have less than equal and not less arrow? And the reason is because they have a completely different meaning. This is an order. It's take the number 1 and put it, and the arrow is put it inside ands. This one is not an order. This is a question. Is it true or false that n is less than 1, less or equal than 1? This is a question. This is an order. Are you smaller? Then become 1. They look similar, but they have different meaning. Don't get confused by the shape of things. Okay. It's the same like we did before. When you have 1 equal sign, it's an assignment. If you have 2 equal signs, it's a question. The same point here. This is an assignment. This is a question. And let's say more. Inside the if, you always want a question, something that is either true or false, because the if should make a decision based on true or false. Okay. And here we are assigning. We are making things. We are ordering things. We're creating. Okay, to find a minimum, I have this example. It's a little tricky, so let's see if we can follow together. You take a vector. It's a function that takes a vector, okay? And the exit condition will be the one that we say. If you have only 1 element, you know the answer. So if the length of the vector that I am storing here in n, if the vector has only 1 element, what is the smallest? The only element in the vector, the first one. Okay? Okay, if you have the vector and there's only 1, perfect. If not, you take the vector and you split in half. Okay? This is from the first until, remember, n is the length of the vector. So from the first until the half of the vector, and this is from the second part, half plus 1, until the end. For example, let's say that you have a good example, 16. 16 is a good example. So here we'll have, let's say that the vector has 16 elements. So we will have 1 to 8 and 9 to 16. Okay? Okay. And then we have only 8. What you do with 8? You separate it and you get, you have 8. How you separate 8? 2 lists of 4. When you have 4, you separate in 2 lists of 2. Okay, and when you have 2, you separate, and then you have the easy case. Okay? So A will be the minimum of the first half, the smallest of the first half. B will be the smallest of the second half. And then you only have to compare these two ones. If A is smaller than B, you know that the smallest is A, otherwise it's B. This is a strategy that works in many problems, divide and conquer. And that is why we teach it, because it's a strategy like, well, we say that decomposing the problem is a good way. One way to decompose is using loops, is the way that I expect you to use in the homework. But in this example here, we are having a different approach in which we take a long list and we separate in smaller lists and we try to solve the problem in a smaller list. So to solve the big list, we separate in half and we solve 1 time, 2 times. To do the half, we do half. You can do it separating in half and half and half until you get only 1. And when you get only 1, you are done. Let me show you a visual show of this, and then we can see the code again. I have this vector, 12, 10, 15, 11, 13. And to calculate the minimum of this vector, here, notice that V is this vector here, and I am including the numbers. This is the index. This is not the content. This is the index. Position 1, position 2, position 3, position 4, position 5. The first element is 12. The second is 10. third is 15, fourth is 11, fifth element is 13. To find the smallest in a vector of length 5, I have to separate in two halves. First, I notice that this list is 5 elements, is bigger than 1, so I have to split. I split in 1, 2, 3, and 4, 5. Then this 1, 2, 3, I also split in 1, 2, and 3. And the 4, 5, I split in 4 and 5. 3, 4, and 5 have 1 element, so I don't need to split them. But the 1 and 2, I have to split. Okay? So every time you have more than 1 element, you split. And if you still have more than 1 element, you split. So you see how the composition happens here. You have a long list and you split in half, and you keep splitting in half, and you keep splitting in half until you get something that you cannot split. Anyway, so we split the problem, the big problem in a smaller one until we get, instead of one big problem, we have many small problems. So now the small problem we can solve it. We know how to solve it. How we solve them? Well, we know the value. This is 12, this is 10, 15. This is the first, the second, the third, the fourth, the fifth element. So this is going to be 12, 10, 15. So the last one are the easy cases, the list of length 1, and it's solved. Now you have to combine them. They have to, how they combine? The code take the result and choose the minimum. Here will be 10, and this is the choosing the minimum of this 11 and 13 will get 11. So you will have here a 10 and here an 11. No? Yes, we got an 11 and we got 10, and the 15 that we had before that we cannot solve yet. Now we have to compare these two, 10 and 15, and you will get 10. And then to do the final step, you have to compare and you get 10. Okay? Let's go back to the code for 1 second. So we see it again. So we say here, this is an internal helper value that n, just to make it shorter, to not write this long text. I given a name to the length of the vector just to make life easier. Otherwise, I have to write this text. It will be harder to read. So n is the length of the vector. If the length of the vector is 1, is the easy case. There were the circles at the bottom. Otherwise, we split in half. And after we get the result from splitting in half, this will take some time to calculate, and at the end you will get A. This will take also some time to calculate, and then you will get B. And we'll get them together, then you compare them, and you choose the best of these two. But you can do it only after this one worked. So this was an answer of the question that we had before, but I agree this is not the first idea that came to mind. And it's not necessarily better in this case, but it can be useful in other cases. This approach, the philosophy, it can be useful in other cases. Another example that I used to do when we teach turtle graphics, we did this kind of drawing. So for example, here the tree was a tree. The definition that we have here was this. A tree is a trunk and 3 branches. But branches are a trunk with 3 branches. Let me say that the point is this. This is a tree of length 1. The small branch here is a tree of size 1. That was the easy one. If your size is 1, you draw 1 line. If size is 2, you draw a trunk and 3 branches. And to draw the branches, well, the branches are a tree of length 1. So a tree of length 2 is a trunk and several trees of length 1. A tree of length 3 is 1 trunk and several trees of length 1, of length 2. This is 4, 5, 6. So here we have a tree with 6 levels that give several trees of 5th level, which get several of 4th level, which get several of 3 levels, 2 levels, and 1 level. And then we play with the angles and the length, and so you can have different shape. And this is some like mechanical because there is kind of the numbers are fixed. But if you put a little noise, a little randomness, they look more and more realistic. In fact, I made a little extension here. In this version, I make it the width of the trunk depending on the level. So This is 6 points width. This is 5. This is 4. This is 3. This is 2. And this is 1. And then I made the color changing from brown to green, depending on the level also. And the angle, well, you can change the angles or something. This is an important concept, advanced concept, and not necessarily something that people understand 100% at the first. The point is that when you do examples, you may find that surprises. So I am giving you a couple of things. I have a homework. There is in order to understand recursion, you first should understand recursion.